I'll see. I don't see.
Yeah, you have to watch it from the side there. Screen, there you go. You see it Purdue pop up?
Yeah.
And then it'll clear.
Mm-hmm.
And you'll just have, there you go.
Okay. Well, hello everyone. We've been talking about PN junctions for the last couple of weeks. So we now understand electrostatics and the depletion approximation. We understand the ideal diode equation and why current flows in forward bias and why not much current flows in reverse bias. What I want to do for this week is to go a little bit further, talk about some non-idealities, talk about some small signal applications of PN diodes, and talk about making diodes in a different way with a metal in a semiconductor, not with a P-type and N-type semiconductor. So we'll dive into it. This is the first of several lectures. This is our familiar ideal diode equation. We've seen the derivation of this. There are two important cases that you should be aware of. There's something that we call the long diode. In the long diode, we inject minority carriers into the P or N region, or both at the same time. They diffuse, they decay as e to the minus x over diffusion length, and we have a factor here that's diffusion constant over diffusion length. Many diodes in practice are short. The length of the region is very short compared to the minority carrier diffusion length. Carriers diffuse all the way across to the contact without recombining. We have basically the same relation. We just replace everywhere the diffusion length by the width of the region. So it's a very simple change. If it's in between, things get complicated. We have hyperbolic functions, but we won't have to deal with that too much. But we want to understand that there are these two limits, the long and the short, and a simple relation in both cases. So this is the plan for the 3 lectures this week. I'm going to talk about several non-idealities of PN junctions today. On Wednesday, I'll talk about small signal models for PN junctions. And on Friday, we'll switch gears and we'll talk about diodes made in a different way, metal semiconductor diodes. Okay, so today, these are the topics. We'll talk about breakdown of a diode in reverse bias. We'll talk about what happens in high forward bias. And then we'll talk about what happens in modest forward bias or in modest reverse bias before the diode breaks down. All right, so here's our IV characteristic again, but now I've extended it to high reverse bias. When we extend it to high reverse bias, you'll remember from 255 that the diode actually breaks down at minus the breakdown voltage. Maybe it's 5 volts, maybe it's 100 volts, it depends on the diode. And in that region, a very large current begins to flow immediately. We actually get almost a constant voltage no matter what current flows as long as we're in breakdown. So you can use diodes in breakdown as long as you limit the current and it doesn't get too hot. You can use a diode in breakdown to be an ideal voltage source, like we learned in 201, a voltage that is almost independent of current. So we want to understand what controls this voltage at which the diode breaks down in reverse bias. So we'll focus on that for a little bit. So remember, we understand devices by drawing an energy band diagram. This is our energy band diagram for the diode under modest reverse bias. You can see that it's under reverse bias because the quasi-Fermi levels are split. And in this case, the quasi-Fermi level for holes, the blue line, is above the quasi-Fermi level for electrons. That's reverse bias. So this barrier height here, this is bigger than it was in equilibrium. It's bigger than Q times the built-in potential. It's bigger by the amount of the reverse bias that we've applied. And what happens in reverse bias is that we have a few electrons on the P side that are close to the depletion region. They sense the electric field. They get swept across. They go down the energy barrier. They accelerate. They gain energy. They lose energy by scattering and lattice collisions with the semiconductor lattice, and that brings them down near the bottom of the conduction band. And we get a little bit of energy, we lose a little bit of energy, the electrons stay near the bottom of the conduction band. Okay, now let's apply a large reverse bias. So this is on my P side over here. If I apply a negative voltage to the P side, electron energy is minus Q times voltage. A negative voltage on the P side means I'm going to raise the electron energy way up. So this is my energy band diagram now under large reverse bias. And now you can see I've got a very large electric field. I have a very steep slope of the energy bands. Any electron, any minority carrier electron that happens to be in the p region that enters this transition region with a high electric field will gain a lot of kinetic energy. When it gains a lot of kinetic energy, now if it collides with the lattice, there's a chance that it can break a silicon bond and free up an additional electron. When it does that, then this initial electron has created 2 electrons. Those 2 electrons are in a big electric field now. They gain a lot of kinetic energy. They scatter off of the lattice. Each one of those 2 electrons can now generate another electron. So there is this multiplication process. One goes in and many goes out. And when you break down, you essentially get at the point where this process goes to infinity. You put in one, and it's like a chain reaction starts, and we just get an enormous number that come out the other side. This is known as avalanche breakdown. Okay. So let's look at it. It all depends on having a very strong electric field in the depletion region so that we gain a lot of kinetic energy, and the electron then, when it scatters or bounces off of the lattice, can actually break a silicon bond and generate more electrons. That's where the increased current flows. So it depends on the electric field. We know about electric fields in depletion regions from the depletion approximation. We remember that the electric field has a peak right at the junction. There's a simple way to calculate that peak. It's related to the square root of the applied voltage. It's related to the doping density. Frequently, we have a one-sided junction where one side is much more lightly doped than the other. Most of the depletion region is on one side, P side in this case. And in that case, the peak electric field is given by a simpler relation. It varies as the square root of the voltage and as the square root of the doping density. Higher voltage gives me higher electric fields. Higher doping density gives me higher electric fields. And when the electric field reaches a critical value where the electrons gain enough kinetic energy that they can begin to break silicon bonds, then we have breakdown. So we just set the electric field to this critical value, E sub CR. And if we know the built-in potential and doping of the p-n junction, we can calculate what voltage the p-n junction will break down at. Right. The critical field is a material parameter. Depends on different, it'll be a different number in different types of semiconductors. So you can also see that the breakdown voltage goes as 1 over the breakdown voltage. If I just solve that equation, it's going to go as 1 over the doping density. The higher I'm doped, the stronger the electric fields are in the depletion region, and the lower the breakdown voltage is. Okay, so as I said, this critical field is a material parameter. In silicon, it's about 300,000 volts per centimeter. In germanium has a smaller band gap. It's easier to break those bonds. The critical field is a little lower, about 100,000 volts per centimeter. Gallium nitride is a semiconductor that people are very interested in these days for power devices, for high voltages. And you can see why. The critical field for gallium nitride is very high. It's about 5 million volts per centimeter. Now, air has a critical field. If you have 2 metal plates and you apply a large enough voltage, you'll get a spark. Or we see lightning when there's a thunderstorm. That's avalanche breakdown of the air. Same physical process. And you can see the critical field for air at sea level is about 3 megavolts per centimeter also. Now, if you go in and say, let's say you're building a power device and you're trying to design the breakdown voltage such that it's big enough for your application. So what you'll do is you'll look at this formula here, you'll pick a doping density such that you can achieve the critical field at a voltage that is big enough for your application. Then you'll go into the lab and you'll find it doesn't work. And you'll say, well, there's something wrong here with what we've learned in 305. Well, we haven't told you everything. And one of the things you need to be aware of is that if you make a p-n junction, we usually do this with this planar process. You open up a window in an SiO2 layer. You introduce dopants, either by diffusion or ion implantation. You heat up the semiconductor and let them diffuse in or undo the damage of the ion implantation, and they move. And there will be a planar junction, and there will be a curvature as it diffuses underneath the SiO2 that was defining where we're making the p-n junction. Now here we need to remember something from 311. The electric field is minus the gradient of the potential. When there's a sharp curvature, there's a sharp gradient. We're going to get much higher electric fields around that curved part of the junction. This formula came from a 1D analysis. This gives me the electric field out here in the planar part. But the device, the diode, is going to break down near the corner where the electric field is the highest. That takes a two-dimensional analysis, and that's more sophisticated. In fact, a lot of power electronic design is about tailoring these fields and smoothing out these curvatures and trying to get the electric field as low as possible. You know, I learned a little bit about this by experience when I had my first job. So I was given the assignment to work on an ion implanter that uses high voltages. We were 100,000 volts. And you know, so there is a danger that you could have arcing and sparks and it could break down. So the ion implanter was manufactured in Boston. I went out to Boston, we tested the machine, everything worked fine. And then we shipped it out to where I was working, which was near Denver, turned it on and sparks were flying everywhere. Okay, so what went on? It worked fine in Boston, it didn't work in Denver. So I learned a little bit. You know, I learned that the breakdown voltage of air depends on the altitude. In Boston, it was about 3 million volts per centimeter. The machine worked fine. It was designed to work fine. But it turns out that the critical field for breakdown actually depends on altitude. It's got a minimum, and that minimum happens to be about where Denver is. Now, if you go to higher altitudes, then you have fewer and fewer air molecules, and it's harder to break down, and eventually the breakdown field gets even higher. But the worst place to be is Denver. So when we flipped it on, the machine that worked fine in Boston didn't work in Denver. So the way we sorted this problem out is we remembered our electromagnetic fields. There must be some high gradient somewhere giving us some sharp electric fields. We came in at night, turned all the lights off, flipped on the switch, and saw where the biggest spark was. Then we turned the lights on, and we looked at that spot, and we found a very sharp piece of metal. Took the file out, smoothed it out so we could round it out and reduce the gradient. Turned the lights out again, flipped on the power. The spark came somewhere else. We looked at the other place. There was a sharp corner there too. Took out the file, smoothed it out. And by doing that, we could smooth out all of the sharp edges in the metal electrodes, and eventually it worked the way it was supposed to. So these curvatures are very important. All right, so that's avalanche breakdown. Many diodes break down by avalanche breakdown, but not all of them do. And we saw that the breakdown voltage is 1 over the doping density. The higher you're doped, the thinner the depletion region is, and the higher the electric fields are. So the breakdown voltage just decreases as you get higher and higher doping. And you can see it depends on different semiconductors because different semiconductors have different critical fields. But if you dope it high enough, what you find is that this linear trend changes. And something happens once you get to breakdown voltages that are less than about 10 volts. There's a different physical mechanism that is causing the breakdown. And that's why the curve changes shape. And what is that physical mechanism? Well, you know, it's something really interesting. It's quantum mechanical tunneling. So you're probably aware that quantum mechanics says that particles behave as waves under the right conditions. A classical particle can't get through an energy barrier. It has to go over the top. But a quantum mechanical particle can tunnel through. There's some probability it can tunnel underneath the barrier and come out the other side. This is known as quantum mechanical tunneling. You only see it when the barriers are really thin. Then particles can go right through the barrier. They don't have to go over the top. Now, how does that relate to p-n junctions? Well, here's our energy band diagram. And we have a barrier between the valence band and the conduction band. The barrier is about 1.1 electron volts. Okay. If the width of this depletion region, the width of our barrier, is very thin, and the heavier we dope it, the thinner it gets, eventually we'll get to a point where electrons in the valence band can tunnel through that barrier and come out in the conduction band of the N side. And then they can flow out to contact and current flows. This is called Zener Tunneling. It occurs when the width of the depletion region is thin enough that this quantum mechanical process can occur. And roughly when the breakdown voltages get less than 10 volts or so, it is probably due to Zener tunneling. So you may have heard of Zener diodes. So a Zener diode technically works on this process, and Zener diodes are often used as voltage references. In practice, this process is known as Zener tunneling after the scientists who first figured it out. In practice, when you purchase a Zener diode, you're really just purchasing a diode with a very precisely controlled breakdown voltage. It may or may not be breaking down due to this particular process. It might be breaking down due to the avalanche process, but people kind of use that term loosely. Okay, so we have talked about breakdown. I want to talk about two other things in this lecture, things that can go beyond the ideal diode equation. So we've discussed breakdown. Now I want to move back to forward bias. So our ideal diode equation describes the forward bias regime. But if we look at forward bias more carefully, we'll find it doesn't quite describe real devices. So the ideal diode equation is this. If I have a significant forward bias, I can forget about the -1. Remember that this J0 term has an Ni squared in it, so it's very strongly temperature dependent. In fact, PN junctions are used as thermometers. I have a homework problem about that because a very small change in temperature will give a significant change in J0, and that'll allow you to use the PN junction as a thermometer. Now, if I take the log of this equation, you can see that if I plot log of J versus voltage, it should be a straight line. And it should have a slope that is equal to, a slope M, I'll call it, that is equal to Q over KT. So just to protect myself, real devices might not exactly be that. So let me introduce a factor called N, which is called a diode ideality factor. N is 1 for the ideal diode that we've been talking about, but not necessarily for a real diode. And the intercept of this plot, given right here, is just J0. So if I plot my forward biased IV characteristic on a log plot, I can use it to deduce what J0 is for this particular diode. And I can see if the slope is right, I know that I'm described by an ideal diode equation. All right, this is a figure from your textbook. This is what a real diode might look like. And if you look at this real diode, you can see there is a region there where the slope is just what it's supposed to be based on our ideal diode equation. But that's just part of the forward bias characteristic. If I go to low bias, that N factor in the denominator of the slope is 2. The slope is not as steep. And if I go to high bias, I also see it start to roll over. So the actual treatment of this can get a little bit complicated. What we want to do is just as the actual treatment of impact ionization and Zener tunneling can get complicated, what we want to do is just get an understanding of basically what's going on here. Now, the high bias regime, two things can be going on: series resistance or high level injection. High level injection gets a little bit complicated, but series resistance is always there and it's easy to understand. So the idea is that any resistor, if I put the metal contacts to contact my diode, I'm going to have some resistance between the metal and the semiconductor. So these big black dots here are the terminals of the diode, but there's really some resistance in series with it. That's R sub S. And that means when I apply a voltage V and forward bias this diode, some current will flow and I'll have a voltage drop across that resistor. The actual voltage that gets into the diode will not be the voltage that I applied. It'll be less. And it'll be less by this amount of the drop across that series resistor. So I just need to fix my ideal diode equation by using the right voltage. Right? Okay. So that's relatively easy to understand. If you look at this regime, you can see that the current is rolling off, and at a particular current, it takes a larger voltage. How much larger? Current times the series resistance. So that's a big factor that affects most diodes. Now things can actually get a little bit complicated up there, and I'll just mention that we've always assumed low-level injection when we've been doing these analyses. Things like the law of the junction, NP is equal to Ni squared e to the QV over KT, that assumes low-level injection. If you really crank the bias up, that might start to fail. And that can be going on up there too in a real device. You should be aware that that might be happening, but the analysis is something that we won't get into in this particular course. Okay, so we've done high bias. Something funny is also happening in low bias. So let's take a quick look at that. So remember when we were discussing the ideal diode equation, we talked about how if an electron that's injected from the N side into the P side, that's a minority carrier electron. They get injected. Anytime they recombine, I get one electron in the external circuit. If a hole is injected from the P side to the N side, it's a minority carrier. Anytime it recombines, I get one electron in the external circuit. So holes and electrons are injected into the N and P regions. They diffuse in, they disappear by recombination, and when they disappear by recombination, current flows. Okay, the question is, what if an electron and hole recombine here? Well, then current is going to flow also. We've ignored that process. We haven't talked about that. Now, one of the reasons that I don't like to call this region around the junction a depletion region, we call it a transition region, is that there really are electrons and holes there, and they can recombine. And when they recombine, we get one electron in the external circuit. So the analysis of this can get a little bit complicated, but let's just get the idea. Remember, when I injected an electron from the N side to the P side, the probability of doing that was e to the QV over 1 KT. That's why we had N equals 1 for the ideal diode. But if an electron gets injected and only goes halfway up, the probability that it will go halfway up is e to the QV over 2 KT. Right? The probability that a hole will go halfway up its energy barrier, which runs down, is also e to the QV over 2 KT. So we can do our little analysis. We know that NP is equal to Ni squared e to the QV over KT. Where these are going to recombine, I have to have an electron and I have to have a hole. So the most of the recombination is going to occur at the point where the electron density is about equal to the hole density. So N is about equal to P. I can take the square root of this expression, and each one goes as e to the QV over 2 KT. Well, the recombination goes as the number of electrons over some lifetime, so I'm going to get my factor of 2 KT. So this is the basic reason that you're getting 2 KT at low bias. Now, something else that's also important to note is that if you look at this expression, the ideal diode part of it went as Ni squared. The N equals 2 part of it goes as Ni. Ni squared is much more temperature sensitive than Ni. So what it means is that if I cool the diode down, this component is going to be more important than the ideal diode component. If I heat the diode up, the ideal diode component is more important. Okay, so we started with the ideal diode part of the characteristic. We've discussed how if we go to low bias, we get recombination in this transition region, and we just get a factor of 2 in the denominator of our current expression. And if we go to high bias, things begin to roll off due to series resistance and high-level injection. Okay, so we understand some non-idealities in forward bias. We've talked about one big non-ideality in reverse bias, that's breakdown. But let's not go that far. Let's look more carefully at reverse bias in the modest reverse bias region before it breaks down. Our ideal diode equation says the current is constant. It's just equal to minus the saturation current, independent of voltage, once the voltage is more than a few kT, so that e to the minus few kT over kT is about 0. This is a real diode, so this is a figure that comes from your book, and you can see this is the reverse biased current. and you can see that it is not constant. It increases with voltage. In fact, it increases as the square root of the reverse bias. All right, so that's a hint. It tells us something about what's going on in this particular diode. So what's going on has to do with recombination generation. In forward bias, we went from an n equals 1 ideal characteristic to an n equals 2 characteristic at low forward bias because of recombination in the transition region. In reverse bias, something similar is going on. So remember, in equilibrium, recombination is equal to generation, so the net recombination is 0. Np is equal to Ni squared. In forward bias, Np is equal to Ni squared times e to the q voltage, forward voltage over Kt. We have more carriers. The system reacts by forcing them to recombine and try to get back to equilibrium. So we have recombination. In reverse bias, N times P is equal to e to the q. The applied voltage now is negative. So there's an e to the minus qv reverse voltage over Kt. That's less than Ni squared. We have fewer carriers there than were there in equilibrium. The system responds by generating carriers to try to get back to equilibrium. If the recombination is less than 0, we have generation. So in a reverse bias p-n junction, we're going to expect to see generation. So this is how to think about it. This is our ideal diode. In reverse current, we have a few electrons on the p side that if they get near this transition region, they see the high electric field, they get swept out, and they go out the n contact. That's one piece of my J0. We have a few minority carrier holes on the n side. If they get close to the transition region, they see the electric field and it sweeps them in the opposite direction. They go out the p contact. That's I0 or J0. That's the ideal reverse saturation current. You can see that it doesn't depend on reverse bias, because if I make the reverse bias bigger, I just make the drop down the potential barrier bigger. That doesn't change the current. What changes the current is how fast they're coming in, and that's fixed. But we should look at what's happening inside the depletion region. Inside the transition region. Inside the transition region, there are fewer electrons and holes than there were in equilibrium. So the system is going to respond by generating more. And what happens is that an electron in the valence band can hop to a defect state in the middle of the band gap, and then it can hop to the conduction band. Now I have an electron in the conduction band and an empty state or a hole in the valence band. The electron drops down in energy and goes out the n contact. The hole drops down in its energy and goes out the p contact. And this generation process gives me more electrons and holes. And you can see that if I reverse bias it more, I have a wider transition region. I have more of this happening over that wider transition region, and I get more current. So when we look at a reverse bias junction, we see that any electron-hole pair that's generated in that transition region is going to lead to one electron in the external circuit. The width of that, or the generation rate, is proportional to Ni over 2 tau. And the current is going to be proportional to that generation rate times the width of the region over which that generation is occurring. That's the width of the transition region, and we can calculate that with depletion approximation electrostatics. It goes as the square root of voltage. So that explains why the reverse bias current doesn't saturate, why it goes as the square root of voltage. It's because the depletion region is increasing. Okay, so this has been relatively fast. If you take the graduate course, you'll spend a few days on each one of these topics. We just wanted to get a sense as to some of the main things that go on beyond the ideal diode equation. And what we'll do in the next 2 lectures is to talk about 2 other topics, but let me just wrap up by summarizing. We began with this ideal diode equation, but we've seen that we have to put an ideality factor n in to make it work in practice. And we also have to account for series resistance if the bias gets big. So the key points to take away are that in forward bias, if you have an electron or a hole recombining in the neutral N or P region, we get current, and we get an ideal current, N equals 1. That's our ideal diode current. If we have an electron and a hole recombining in this space charge region, this transition region, we get current also. But the N factor is 2 in this current expression. In reverse bias, if we're dominated by electrons and holes in the neutral region being swept through the transition region, we get a constant current, minus I0. But if we're dominated by these recombination processes in the depletion region, then our current is not constant, it increases with reverse bias. And when we really crank the reverse bias up, every diode will eventually break down to one of two processes, Avalanche Breakdown or Zener Tunneling. Okay, so we will continue and talk about some other aspects of p-n junctions in the next lecture.
Hit the stop button right there on the screen.
Where?
Right here.
Oh,
Yep,
all right.
there you go.